Because we're doing estimation and we're creating samples, it's pretty obvious that we're going to have some difference between the sample and our population. Now, an easy way to think about this might be to consider that we have 100 test scores and we sample 20 of them. The average test score in that sample might be different than the average test score of the entire 100 that we had in our population. And if you took another 20, those two samples might be slightly different as well. But they should be close to the entire data set, just not exact. This difference is known as the error. And there are two primary types of error. There's the sampling error, which is the amount of error caused by the sample being slightly different from the population. This is just random chance error. We take our sample, and the difference in our mean, for example, is just slightly off from the population. There's nothing wrong with the sample, it is representative, and everything else that we did was fine, and it's just a random chance of being off. The non-sampling error is caused not by the sample, but rather by errors due to the observations, such as the respondents themselves, or data points, bias caused by the analyst, or some other bias that's introduced into our sample. Non-sampling errors are a big problem, especially when conducting surveys or conducting any type of research or trying to assess something that's going on from some observational data. The first one is poor representation. These are errors that occur from a heavily biased sample, such as having a survey with only one male respondent and trying to infer an analysis from the whole population. It would obviously be biased to, say, female, and if you're trying to assess it to the whole population, you could be missing something. This would be catastrophic if we were dealing with medicines, because there might be difference between the reactions for males on the medicine as there are for females. Another type of error are response errors, and these response errors are due to the individual respondents themselves. So, for example, non-response bias. Respondents who choose not to answer all the questions in a survey, which lead to incomplete data. Consider having a survey where you have 10 questions, and all 10 questions are somewhat related, but some people choose not to answer 3 or 5 of the questions. It could affect your overall connection between any 2 questions, 3 questions, or 4. Another type of response error is non-truthful responses, where respondents are deliberately answering incorrectly or providing a response that the respondent believes the surveyor wishes to hear. So the respondent may not want to state who their political preference is for a politician because they believe the respondent is going to act in a negative way. It can also be where the person who's conducting the survey, if they do it in person, provides a feeling to the respondent that they should be answering in a particular fashion. We also have indications of method bias, and method bias occurs when answers given vary because of the method used. We may know this because we may be more inclined to answer one way in person than we are, say, via social media, and this is a method bias. Survey or measurement bias occurs when responses provided don't match the intended questions of the survey that it was trying to measure. So, for example, the respondents answer what they believe is truthfully, but the survey questions were worded in such a way that they were interpreted incorrectly, and thus they are not matching what the intended analyst was hoping to understand. Another problem is data collection and storage errors. These are just natural errors in terms of the overall process. They occur due to bad collection methods or errors in entering the data. So we know that sometimes people misenter or key in incorrect information. And sometimes we end up with corrupt data that occurs from various sources or various systems. And even sometimes systems accidentally will change information due to bugs in their data collection methods. When we collect our sample, we have a few key things that we need to know about our sample and its relationship to the population. First, we need to recall that we need to describe our population. And for the purposes of these slides, we're going to assume that everything from this point is a normal distribution. That means that the population set of data will be normally distributed, and it will have a bell curve, and we can describe this normal population with 2 specific parameters, a mean and a standard deviation. If we have a sample of this data set and we assume that it is representative of this population, so if we have a sample from this data set, say of voters, we assume that it's going to come from the same population or from a population of voters, say in the United States. From this sample, we will create what's called a point estimate. And the point estimate is an approximation of a population parameter. So the point estimate for the mean, which is mu, and standard deviation, which is sigma, is created by taking the mean and standard deviation of the sample itself. And so what does this mean? Again, the point estimate is an estimation. If we have our sample and we calculate an average, we say that this is an estimate of what the population is going to be. And its standard deviation of the sample will be an estimate of what the standard deviation of the population should be. Now, we know that there is very likely going to be a difference between the point estimate and the population parameter of that same estimate. This difference is called a sampling error and is also referred to as an estimation error. Now, let's take an example. Let's assume if we have our point estimate from a sample, but we collected another 100 samples and we calculated their point estimates. So let's assume the data set is a lot larger than 100 observations. Let's say it's 100,000 observations, and we collected 100 samples. We would then have 100 point estimates for the mean. Now, if we think about it, the more estimates we have, the closer, if we average those, it should be closer to the population mean because we're adding more and more samples and sample data together. So let's assume that we have 10 samples from different classes and we assemble the average grades in each class. It might look like this set of data. Now, all of those averages together, especially as you collect more and more samples, will have its own distribution. They're forming its own data set. And we call this the sampling distribution of the point estimate. So this is the distribution of the point estimate. Now, a principal concept of any analysis of point estimates is, well, how good is the estimate against the population parameter itself? Remember that if we have a good sample, it should give us a good estimate of the population mean, but we're likely to be off, just hopefully not by too much. What we want to do is create a confidence interval. This confidence interval is an upper bound and a lower bound by which we have a high degree of confidence or certainty that the population parameter lies between. And we'll see in other slides how to calculate this confidence interval. But more on the estimates, let's consider the fact that we have a number of point estimates for the sample. These samples will give us a sampling distribution for the point estimate. An unbiased estimate is one in which the mean of that sampling distribution is equivalent to the population parameter being estimated. That means that the mean of the sampling distributions, if we had all those samples, and we aggregated the information and we took the mean of that information, that it was identical to the population parameter. And we therefore call that an unbiased estimate. So what does that mean? That means that the samples that we have as we collected more and more samples and we had our distribution, that the mean of that is identical to the population mean. There's no bias at all introduced, and so that's why we call it an unbiased estimate. Anything that is not unbiased is considered a biased estimate. But for the purposes of these modules, we're not going to be worried too much about unbiased or biased estimates. The sampling distribution described above also has a standard deviation in addition to the mean. And this standard deviation is considered the standard error of the estimate. So in other words, when we calculated the 10 sample means for the class, when we calculated the 10 sample means for the average scores, it has a mean, but it also has a standard deviation. This standard deviation is considered the standard error of the estimate, and we will use this extensively.